Assalamu alaikum. How you doing, guys? Today I'm gonna continue on the serviceability part, and we're gonna tackle the deflection control. So, why do we care about deflection? Well, if we have excessive deflection or large deflection, then that can lead to the following. Number one, what we call an visually offensive sag. So let's say if this is the center line of my beam and then I have a large deflection like that, then this maximum deflection usually we also go sometimes as sag. Okay, so we probably would not like to see that in buildings, of course. That sag, for instance, or even sometimes it's not that big, could actually lead to damage to supported walls and partition. As you know, let's say if this is part of your beam, this is my column over here, and then there is another part, and then usually here we have under this beam partitions or the walls, right? So sometimes what would happen if we have large deflection over here, this would actually influence these partitions. So if they do not, they're not strong enough, and usually they're not, then that will also lead to cracks in the walls, and we do not want that or like that at all. Then for fitting of doors and windows, I don't know if you noticed, even let's say some of your relatives, they start complaining that doors don't close anymore, windows are hard to close, sometimes they even break, and that usually happens after what we call long-term deflections, or not even that sometimes if the design is poor and we have those openings for the door and windows, and then even after we remove the shoring and we try to put those doors in, you've noticed sometimes that they don't fit, and that's also due to deflections. The misalignment of sensitive machinery and equipment, we usually have that in labs where we are measuring some sensitive, let's say, dimensions, sometimes in the order of micron, macrometers, or millimeters even. So if the building is off, then the measurements will be off too. So buildings like labs, plants, then we have to be very careful of how we design for deflection. Affect the structure appearance. Obviously, if you see a structure that is a little bit tilted or there are more cracks visible, then again, this is something that you do not want. And the most important thing is frighten the occupants of the building. I probably would not live in a building where I can actually see visible cracks in the walls or in the beams, or maybe again, going back to the visually offensive sag. So these are one of the things that will make us want to control deflection and minimize it as much as we can. Again, going back to the word deflection control. Now, there are two types of deflection. Type 1, which is the immediate deflection, and this is what we call upon the application of load. And let's say after we have the shoring in and we remove the shoring, then if again the design is not adequate, sometimes you could actually see the deflection right away. And this immediate deflection, we can calculate it based on the elastic uncracked cracked member or combination of both, and I will talk about the combination later on, but we already dealt with the uncracked and cracked members as we have in both when we did the calculation for the width of the crack, and we did that mainly also at the beginning of the course when we talked about the flexural strength of members. Long-term deflection, and that's a deflection that continue over several years, and that is usually due to creep of concrete that settles in after a while. Okay, and we will be showing you how to calculate that. Now, this deflection is based on the loading on the beams or slabs itself, and it is separate from foundation settlement. Okay, so foundation settlement, if it happens, is an added deflection, but we're not going to talk about that, and this is left for some other classes, courses. So we will not be tackling this in this class. Now, how do we calculate the deflection? Well, we have two approaches. One is an indirect approach, and that we do by setting upper limits on the span depth ratio, and I will show that to you in the next slide. And the direct approach is to actually calculate the deflection and then compare that to some specific limitation which is imposed by the codes or special requirements. So in the ACI code, which we follow, there are some limits on how much the maximum deflection is, but certain, let's say, customers would give you even more stringent requirements and say, okay, we think that the maximum deflection proposed by the code is not adequate, and that's fine. Okay, but then they have to tell you what that limitation is, and then you have to design your building accordingly. Okay, so let's start off with the indirect approach. Indirect approach, the good thing about it is that you really don't need to calculate any deflections. Okay, and this is divided into two parts. First of all, if you look at this table, and this table is kind of the summary of the ACI code section 7.3 and 9.3. 7.3 talks about the solid slabs, and 9.3 talks about beams and one-way joist or ribbed slabs. Okay, then the limitation are, and by a minimum slab I mean the H minimum. Okay, so that's the minimum thickness that you need for you not to calculate the deflection. So if I have a simply supported beam, then for a slab this is L over 20, where L is the length or the span length. If it's a beam or one-way joist, then it's going to be L over 16. If we have one end continuous, then this is going to be L over 24 for solid slab, and L over 18.5 if we have beam or one-way joist, and you get the pictures. Now, here is some modifications that we need to do. So if we have lightweight concrete, and the density is of the range from 1,440 to 1,840 kilograms per cubic meters, then the values, and by values I mean these, of course both, they should be multiplied by 1.6 minus 0.03, the density, and that should be more than or equal to 1.009, which means this is the minimum number that you can do. So let's say if I have density of 1,440, then I take this number and plug this into the equation and see what that factor is. So let's assume it's less than 1.09. Then now my new H minimum would be L over 20 times 109. Okay, so that takes care of the density of concrete. So if we have normal density, then you don't need to do any of this. I mean by that. Okay. Now going to the reinforcement for the yield strength. So if we have any other value any value than 420 megapascals, then we calculate a new one, and that number is 0.4 plus Fy divided by 700. So let's say I have a grade steel of 550, then my new factor would be 0.4 plus 550 over 700. Okay, so maybe that's close to 0.8. Then this might be approximately 1.2. So then I multiply these values by 1.2. But if I have normal weight concrete, Fy is equal to 420, I don't need to do any of these modification factors. Okay. So let's talk a little bit about examples on how to use this table. So let's say I have a beam. Oops, this is beam. Okay, so let's say we have a beam like this, and this is simply supported, and let's say the length of that is 3, then my H minimum would be simply, if that's a beam or a one-way rib, it would be simply L over 16, or 3 over 16. And that would be 18.75 centimeters. So if I am designing this beam, I probably will take H to be equal to 20 centimeters. So this 20 centimeters is due to the deflection part. So now if I'm designing this for flexure, I find out that the 20 is not sufficient for flexure or shear design, then you probably will have to increase H. But as far as deflection control is telling me that my minimum H, or this beam right here, it's going to have an H of 20 centimeters minimum. So if I, let's say, due to flexure and shear, H got about to 50, that's more than 20, then I'm fine, which means for this beam, I really don't need to do any deflection calculation. So that's what the indirect method means. Let's assume we have a beam like this, and this is what we call one end continuous. So let's assume that this is, well, I'm pulling numbers. So this is, let's say, 4 meters, and then this is, say, 5. So this is one end continuous. Then H minimum for that would be equal to 4 meters over 18.5. Okay. And for this one, again, this is one end continuous. Okay. And this would be 5 over 18.5 as well. So this gives me 27 almost centimeters, and this gives me almost 21.6 centimeters, and this is centimeters. So out of these two, my H minimum is equal to the largest of them, which will be 27, but then for design purposes I probably will choose 30 centimeters again. So this H is the minimum H that is required for deflection. Okay, again, in the design now, you used to design for flexure, we designed for shear, now we are going to design for deflection. So if the 30 centimeters is enough for flexure, good. If it's not, then we have to increase H. But all what we need to know, all the information that is good for me here right now here is, okay, if I'm using an H of at least 30 centimeters, I don't need to do any deflection calculation. I'm going to do one more example. Just let me get rid of this right here. It's taking some time, sorry about that. I think this is enough. So let's say I'm going to use larger beam. Okay, again, drawing is not. Okay, so let's say I have a beam like that, and let's assume that this is 3 meters, 4, and then this is 3. Again, this is for beams and rib slab. You can apply the same to solid slab. It's going to be a little bit different. The coefficients are going to be different. So now for this part right here, this is again one end continuous. Then H minimum would be 3 over 18.5. This one right here has both end continuous, right here and right there. So for that, it's going to be 4 divided 4 divided by 21. Again, now this is one end continuous, and then this is also going to be 3 over 18 and a half, right? So for this one, this is going to be 16.2 centimeters. This one, 4 over 21, is going to be 19. So H minimum, according to that, is going to be 19. So for design, I'm going to use here H is equal to 20 centimeters. Again, this is due to deflection only. You still have to check against shear and flexure. So I hope this is kind of showing you how we calculate the thickness by what we call the indirect means. Okay. Moving on to the immediate deflections, or this is the part where we actually are going to calculate the deflection. So the question might be, why am I going to calculate the deflections if I have the previous method, which sounds a lot easier? I agree with you. Again, because we're engineers and we're lazy and we don't like to do stuff that much. But again, so let's assume that some customer is telling you, well, I really don't like the deflection imposed by the code. Then you have to come up with the actual deflection and compare that to his standards, let's say. Or the other part where this really becomes more apparent. So let's say you are designing the slab of a building, and then you use the H minimum technique, and you found out that for 90% of your slab you need, let's say, 25 centimeters, and for only 10% you need 30 centimeters or 31 centimeters if we're talking about slabs. So there's a difference in about 7 centimeters, and then the question becomes, is it fair to impose that 10% over the whole slab? So in that case, you probably would assume that you're going to take the minimum value, but then you have to calculate the deflection to make sure that you are within the limits. So these are the two things where I think it might arise where we actually need to calculate the deflection. So how do we calculate the deflection? So if you remember that the deflection usually is a function of load, span, supports, and then that's divided by EC, and here I. Either I is the uncracked transformed, or it's the cracked. And if you remember, if we have let's say a distributed load like this, then delta for that was 5WL to the 4 divided by 384 EI. Okay. Now, when we had, let's say, a concentrated load, okay, then this was, delta was something else. And I don't remember what the equation was, but, oh no, wait a second, I do remember. It's PL cubed over 48 EI. Okay, so the one thing that is constant is the EI part, as you notice, but what is different is that coefficient. So for distributed load, that was 5WL to the 4. For a concentrated load, that was 5PL cubed over 48. So that's what I mean by a function of loads, spans, and supports. Now, obviously, if it's a continuous beam, then that whole scenario is going to be different. Now, the other definition that we had back from the flexure course was the cracking moment, and for that we said this is equal to F rupture, which was the modulus of rupture, or the strength in concrete under tension or before developed cracks, multiplied by I uncracked transformed over YT. So that was the equation that we used to develop the cracking moment. So as you can see here, I'm still putting ACI 14, and here I'm just going to point out the difference between 14 and 19 because there is a difference in both the use of equations. So in the past, before I get to that, if we go to this chart right here, then you can see I have two limits on the moment of inertia, or the second moment of area. One is the cracking, and one is the uncracked transformed, right? And as we said in the past, when we were designing for lecture, it's hard to keep up on when the section cracks or doesn't crack, and then so we assume that the whole section under the neutral axis is cracked or it does not exist. Now, for deflection calculations, this is not the case. So we impose what we call an effective moment of inertia, and that is between the I uncracked, the uncracked transformed, and the cracked moment of inertia. Okay, and here where MA here is the maximum moment on the beam divided by the cracking moment, and this shows you the relation between the uncracked versus the cracked. And the way that we calculate IE is through this equation, or let me say used to. Okay, so we do not use this equation anymore. Okay, now what we do use is the new equation, which is again changed in the ACI 19 code, and here the form of the equation for the effective moment of area is different. Here we have limits, so if my maximum moment is less than 2/3 of my cracking moment, then my effective EI is equal to the gross moment of inertia. And what I would like to say at this point, that we stopped using we're going to stop using the uncracked transformed section. We are just going to use the gross, which means I gross is just, let's say if I have a rectangular cross section like this, okay, still I have, let's say, steel, then for this case my I gross is simply going to be BH cubed over 12, and I'm going to ignore the steel that is present here, or even if I have steel here as well, this is also ignored. So for me, it's just going to be the gross moment of area of the section. Now, if my maximum moment is larger than 2/3 of the cracking moment, then I'll be using this equation for my I effective. Going back to my cracking moment, this is now still the rupture, and here again I removed the I uncracked transformed by just using the gross moment of inertia, and again Y is the extreme fiber at the top of the compression member. Okay, now this curve shows me the difference between IE of old, this is being the 14, and new is being the 19, and here you can see that I effective now is smaller than what it used to be. Okay, it's like we pushed the curve in this direction. After a certain point here, it really doesn't matter what code you use. Okay, it's going to become more of a cracking moment. So the only change that is happening is kind of from this point to that point. Okay, so it's telling me that if the maximum moment becomes 3 times the cracking moment, it really doesn't matter. The present, it's not different from the cracking moment of inertia. Now, so how we are going to use this? So let's say here in that plot, I am plotting the maximum moment versus the deflection. As you can see, this curve is non-linear in nature. It's only linear up to the cracking part. So let's say I'm interested in calculating the deflection due to the live load only. and that happens a lot since and I will say more about that when we go to the long-term deflection part. But let's say if I only want to know what the deflection is due to the live load only. So for me to calculate that, I need to calculate the deflection due to both the live and dead load. Okay, and I'm going to call that delta 2 because this is going to have a maximum M2. Then I'm going to calculate delta 1, which is due to the dead load only, no live load. Okay, then that deflection due to the live load is simply delta 2 minus delta 1 again, and that's due to the nature of the nonlinearity of the material, number one, and also in the equation of the moment of inertia, of the effective moment of inertia, as you noticed on the slide before, and I will show you an example as to how to do that. Okay. Now, as I said, if I'm calculating the deflections, then I need to know what the imposed limits are, and these limits are as follows. So here I have, let's say this is my member. If I have flat roofs, then not supporting or attached to non-structural elements likely to be damaged by large deflection. So if it does not support non-structural elements and are likely to be damaged, okay, then the deflection to be considered is immediate deflection due to the maximum of the live roof load, snow load, or rain load, and that should not be more than L over 180. If I'm only concerned about immediate deflection due to live load only, and that's for floors, okay, again, we have roof and then we have floors, all right, then that limitation is going to be L over 360, okay. Now, if it is supporting or attached to non-structural elements, okay, one, if it is likely to be damaged by large deflections, then the part of total deflection occurring after attachment of non-structural elements, which is the sum of the time-dependent deflection due to all sustained load, and all sustained load means dead load, and the immediate deflection due to any additional live load, okay? So here, in this case, or for that part, I need to calculate the sustained deflection, the deflection due to the sustained load, plus the live load, okay? And here I have, again, two limits. Limit number one is L over 480 if those structural elements attached are going to be damaged. If they are not going to be damaged, then I'm going to kind of relax the limitation and say this is L over 240, which goes back to the drawing that I started off with, which is this, and I'm talking about the those partitions or blocks that we call them, okay? So some of these blocks actually might be strong enough to withstand the deflection. If they are, then that beam right here, the deflection or maximum deflection allowed is L over 240. Now, if those are, let's say, if they cannot handle the deflection or they are not strong enough, these partitions, then the maximum deflection allowed is L over 480. Okay, so these are the limitations set by if I'm calculating the immediate deflections. Now, one more thing regarding the values of the effective moment of inertia. So this part is telling me if I have a continuous one-way slab or beams, okay, and beams, then IB can be taken as the average value for the critical positive and negative moment section. So if I have, let's say, continuous beam or slab for that matter, let's say something like that, and you know that the moment diagram is something like this. So I could simply take, let's say, this is my critical positive a moment, and let's say this is my critical negative moment, then IE can simply be the average of this one here and that one here. So this one plus this one for the whole beam. You can, okay? Or if you want, the other option would be, again, let me draw something similar to this, and this is a continuous beam. So here, let's say I have IE in the middle. Here I have IE1, for instance. This is IE2, for instance, and this is IE middle at midspan as well. Okay, so for this part, when I have two end continuous, one suggested average could be IE is equal to, let's say, 0.7 IE midspan plus 0.15, and let me erase this. Okay, IE1 plus IE2. Okay. Now, if I may be talking about this span right here, which is what we call one end continuous, then one form of the equation might be I effective is 0.85 I mid plus 0.15 IE1. Okay, again, these are average values for the moment of inertia. If I have just a simple span like this, then IE is just I mid at midspan. Okay, right here. So these are some of the average values that we can take for the value of the effective moment of area. One more thing is how I'm going to calculate the long-term deflection. Well, the long-term deflection is I take that deflection that I calculated due to the sustained dead load, and then I multiply this by that factor, and this factor is equal to Xc, which is a time factor, which I'll show you in the next slide. Rho prime is just simply the reinforcement of the compression area, which is just simply I prime S over BD, provided we have compression reinforcement. The factor Xc is if this load is sustained for 3 months, then I multiply this by 1, 6 months 1.2, 12 months is 1.4, then for 60 or more I multiply this by 2. If you need any duration between those two, you can just do regular interpolation. So let's say if I want 9 months, which is somewhere in the middle, then this is probably going to be 1.3. With that, I'm going to solve an example, and this is actually a question that I asked in the second of last semester. I have a beam giving you the values of Fy is equal 420 megapascals, F prime C 22 megapascals, modulus of elasticity is equal to 2,487, the rupture stress is 3.25, and the modulus of steel is 2 times 10 to the 5 megapascal. And what I want is the following. Is the deflection calculation necessary? Why? Calculate the instantaneous live load midspan deflection, or I want the deflection due to the live load only. Okay. Now the beam that I have is 8 meters in length. My dead load is 4 kilonewton per meters. My live load is 8 kilonewton per meters. Okay. The section that I have, the height, or D, excuse me, is 522. And the center from the bottom is 78, which makes the total height of 600 millimeters. I have 8 by 20, and the width is 350 millimeters. Okay, so starting with part 1. Now we know for simple beams, H minimum is L over 16, L is 8, divided by 16 is half a meter. H provided, which is here, is 0.6 meters. So I am not required to do any deflection calculation. But since I was asked to do it, I have to calculate anyway. But as far as not using deflection, as far as not calculating, it is not needed. So that's the answer right here. It's not required because of this. Okay. Now we're going to start the second part, is to calculate the deflection due to the live load. So to do that, I'm going to start off with calculating I gross. I gross is simply 1 over 12 B, okay, which is 0.35 times H cubed, which is 0.6, and I get 0.063 or 63 meter to the fourth. Now I need to calculate rho. Rho is the area of steel of 8/520 divided by B times D, and it's 0.01376. And using the same equations that I used for the crack example and the examples that we used in the first part of the course, I'm getting K equal to 0.372, which is giving me my Y. Again, this is my Y, what we call YT, is equal to 194.1 millimeters. So now I can calculate the cracking moment. The cracking moment is simply 1/3 B H cubed, okay, this part, plus 8, which is my N, which is again the modulus of elasticity of steel over concrete. This is my area of steel, so I'm taking this area right here, the full 8. Here I'm converting it to meters, excuse me. D minus this part, so I'm taking the moment again about the neutral axis, over 1,000, again converting to meters, square. Okay, here I'm using the parallel axis theorem, again like we did before. So this is equal to 0.00305 meter to the 4. So now I have I cracked. Now I need to calculate the cracking moment. Cracking moment again is F rupture times I gross divided by Y or H over 2, okay, and that's equal to 68.25 kilonewton meters. Again, here because I'm using the gross I, then I'm using the H over 2, and I'm not using the one for the cracked section. Please note that, okay? So this is H over 2. So 2/3 of that, of the cracking moment, I mean, that's 45.5 kilonewton meter. Okay, then the maximum moment due to both dead loads and live load is equal to 4 plus 6 times 8 squared, which is the L over 8, and that's equal to 96 kilonewton per meter, and that's larger than the cracking moment. So I have to use the second part of the table, and my effective moment of inertia would be I cracking, which is this. 2/3 of M crack, which is that 45, maximum moment is this, and then the I cracking is this value right here, and I gross is this. So my I effective is 0.003415. Plug that into the deflection equation. So the deflection due to dead load plus live load is 5 times 12. Again, you've noticed I did not use any factors load, because for serviceability calculations, factored loads are not allowed. I'm only using service loads. And the 12 is simply the dead load 4 plus the live load 8, divided by 384 times E times I effective, and the total deflection is equal to 7.54 millimeters. And that's less than, I'm assuming here that partitions are likely to be damaged. Then this is my L over 480, and I think this value is around 16 something millimeters. Okay. Now again, this is total deflection. I only want the deflection due to the live load. So now I calculate the maximum moment due to dead load only, and that's equal to 4 times 8 squared over 8, and that's 30 kilonewton meter. Now that's less than 2/3 of the cracking moment. Then at that point I can just simply use I gross in the deflection equation, which I did over here. So now the deflection due to dead load is 5 times 4 times 8 to the 4th divided by 384. This is being my E and I, and this is 1.36 millimeters. So the answer would be that deflection due to live load is equal to 7.17 millimeters. Okay, here I'd like to point out, so if I was asking you what is the long-term deflection after 5 years, for instance, okay, so if I ask that question, then you still have to do the same steps, because in that part, that the delta long-term, okay, and we know we don't have any compressive reinforcement, so that rho prime now is equal to 0, right? Then XC for after 5 years is equal to 2, then the long-term deflection would be equal to 2 times, this is now due to the sustained dead load, okay, so times 1.36, plus the deflection due to the immediate life load, which we just calculated to be 6.17. So this answer right here, let's say this is 1.4 times 2, 2.8, 2.8 and 6, that's 8.8, 17, this is around 9.07 millimeters, okay? Still less than the L over 480 millimeters, so this design again is, and we knew it would be because we chose our H more than the H provided in the table. And this will end the this portion of the class. You guys have a nice day and stay safe.